All right. My name is David Golden. I'm an employee at Heroku. I'm going to be talking to you today about the Celery Canvas module. Celery ships with a lot of tools to compose tasks together into workflows. But as I've talked to people about their use of Celery, a lot of people are either unfamiliar with these tools or they're afraid of them because they're not quite sure how they work, or they don't really trust them. So my goal today is to kind of pull back the curtain, show you what's going on with these workflow tools, and show you how you can even extend and create your own. But before we get to that, I want to talk about some design principles of Celery tasks in general, apart from the Canvas workflows. In my opinion, a good Celery task is atomic. In a concurrent system, you don't want to be leaking intermediate state out to other parts of the system. So you should have clear success-fail scenarios where any state that changes as immediately as possible, and only when the task succeeds. That keeps your tasks from interfering with other tasks or other parts of your system. I think tasks should also be idempotent. Tasks will fail in creative ways, whether you lose a process or an API goes out or something like that. You want to be able to pick up where you left off and be able to execute your task over again so that you don't have to have manual intervention when a task fails. If your tasks are idempotent, you get this for free. And for the purpose of our workflows, tasks should be composable. This is the same as it is in functional programming, that you should think of your tasks like a function that have one concern, take arguments for all of the state they need or ways to access that state, and return something that's useful for other functions to consume. So a lot of people focus on their choice for the Celery broker, but they overlook the result backend as an architectural choice. The result backend is really important for these workflows, so it's worth taking some time to talk about what it does and which one you should choose. First of all, the result backend is in charge of tracking task state. So when a task is sent to a broker, Celery marks the task as pending. When it's then started by a worker and marked started, success or fail. You need a result backend in order to know what state a task is in, and of course to know what it returned, what value or object the function returned that the task was running. So which backend should you choose? I implore you, if you take away nothing else from this talk, please do not use RabbitMQ as your result store. What's actually going on here is that Celery will use a message queue in Rabbit because that's Rabbit's only tool, so everything looks like a queue to Rabbit, as the result or state. And when a client asks for that result or state, Rabbit will actually dequeue the message from the queue. The person who's asked, or the task who's asking, will consume that, and the next one who asks will get nothing. There's nothing to get. So the next time you ask for the task state, it says, I don't know, it's pending. You can also use a database for your result store by using Django Celery, and the Django ORM models are provided for results, but pulling in a database can be kind of expensive, and it doesn't support all the operations that make our workflows work well, as we'll see later. Also, if you happen to be unfortunate enough to be using MySQL, you could have problems from your transaction isolation level, where one process sees one answer and another sees another for what state am I in. Memcache is a pretty good choice for result backends, but it's not persistent. So if you care about your results sticking around when the process restarts, then Memcache is probably not your best choice for result backend. It does, however, have atomic counters, which are nice. It supports expiry for keys, because you don't want your results to be hanging around indefinitely, forever. But that persistence problem causes me to want to choose Redis normally for my result backend. It has all the same properties as Memcache with the exception of sharding, but you can usually keep it pretty persistent. You could lose a little bit of data, but generally not much. All right, so now let's get to the actual building blocks for Canvas itself. The most fundamental building block of the Celery Canvas tools is the signature. It's important to remember as we go forward that everything in the Celery Canvas module is based off of signature. So what is a signature? A signature is simply a serializable representation of a task. It is a subclass of a dictionary, and so it contains the import path for the task itself, any arguments and keyword arguments that are needed to be passed to that task, and other options. So you see we can JSON dumps a signature, and then signature also takes, and it's in it, a dictionary. So we could dump it, load it back in, pass it to the signature to rehydrate a signature, and you can see how this would be useful when passing, across a message bus, consuming the other side. This is basically how task serialization works in general. So when you send a task over the wire, it's always creating a signature, always passing that signature through the message broker and back to the worker to be consumed.
What was the subtask type?
I'm sorry?
What was the subtask type there in that JSON?
Subtask type we'll get to a bit later, but for normal tasks, it's none or null. For the workflow types, which aren't actually a task, but they're a serialized representation of a workflow or a group of tasks, the subtask type is a key that tells Celery which type of registered signature to use in order to reconstruct this signature object. So there's a mapping in Celery of the subtask type to the signature class, and if it's null, it just creates a normal signature class, but if there's something like chain or group in there, then signature knows about those registered types and uses that subtask type to key off of which signature subclass to rehydrate. There are convenience methods provided on signatures in order to treat them much like you would tasks. Those pass through normally to the task if it's just a single task signature. So you can run delay, you can run apply async. There are also convenience methods off of tasks themselves, which you can use to get a signature. I think in Celery 3.1 it's still .subtask, but in 3.2 it's .signature, or .s for short works in both 3.1 and 3.2. You can pass those methods, arguments, and keyword arguments that are then stored into the signature and serialized. You can even kind of build up arguments and continue to add arguments and keyword arguments, with the exception of immutable signatures. So signatures can be marked as immutable, and then their arguments are frozen. This is useful in situations where something else is trying to add task arguments for you, as we'll see later. And if you want to prevent that from happening, just make your signature mutable. So now that we are able to serialize tasks, we can begin to compose them by constructing tasks that interact with other tasks. The most simple unit of composition is a callback, which is a task that is launched based on another task finishing. The result of the parent task is passed to the child as that task's first argument. So you can see here we have a couple of signatures for a task that just adds numbers together, but the second one only has a single argument. When we call this .link method on the signature, you can see then when we convert it to a dictionary, the link option is set to the list of tasks that are linked to it. And so Celery, when it finishes the first task, will say, okay, are there any linked tasks for me to run? And if so, I'm going to run them and pass my result as an argument into that next task. So here, the result of the child task is 6, 1 plus 2 being 3, then added to 3 being 6. But the result, async result object we get back from actually applying async on the original signature is the parent task's result. So result.get will be 3, and then we have to navigate down to the children property to see all of the dependent or child tasks and navigate to its result to see the result of the callback task. We get one step farther down with chains. So chains are multiple tasks run in series, and they are actually chained together via this callback mechanism. So think of a callback being, one task launches another. A chain is one task launches another for as many tasks as you specify. So when we construct a chain, we can give it any number of task signatures. You can see that when we cast it to a dictionary, those then get put into a task's keyword argument. The result from the chain is actually the async result of the last task in the chain. That's an important distinction because then the way you treat that result is different than you would for a normal callback. It makes sense for a chain because when you chain things together, you're saying basically this is a set of dependencies on the last task. And so you really want to know, what is my end result? And so Celery passes back to you the async result of the last task in the chain. And if you were to inspect its state, you would see pending, pending, pending while the other tasks in the chain were executing. But it would have populated the parent properties, so you could navigate using .parent, .parent, .parent kind of back in the chain up to the very first task and kind of inspect the state of the chain as it's being executed if you wanted to. So what's going on under the hood here, these are not complete code slices, just as much as I can fit on a slide, is that when you run the chain, it's actually going through a process to prepare all the steps by navigating through each of the tasks and assigning the task to the link of the previous task. So it's taking the task before it and it's saying, I want to link it to the current task, and that creates this chain of callbacks. Remember, .link is the way that we assign one task to be a callback of another. And so then that prepare steps returns all the tasks and their async result instances, and the run method just takes the first one and calls apply async on it. It's kind of like lining up all the dominoes and then just tipping the first one over, and all the other dominoes, continue to fall in series. So next after chain, we have group. Group is entirely different. It's not built on callback or chain, and it's intended for a group of tasks that are meant to be run in parallel as opposed to in series. Now, one important distinction and difference between group and chain is with chain, you care about the last result in the series because you want the end result. In group, all of the tasks are treated as equals because they're all run in parallel. So what Celery decided to do was to create a new async result subclass called group result, whose .results or .children, they're both the same in group result, represent the async result instances for each child task. The group result, you notice, has its own UUID that is distinct from any of the UUIDs in the child tasks. That is important because normally when you ask Celery for the result or state of a job, it uses the task ID, the task UUID, and it will track that in the result store. But there is no state for a group result because this UUID doesn't actually map to a task that's being executed. It's an abstract concept for a group of tasks that will be executed. So you can see here the serialized version looks very similar to a chain. The only real distinct difference is this subtask type group. So, the signature is registered as a type group. Celery sees that group and rehydrates it as a group instance. So if we iterate through the child results, we get the results of each task. There is a bit of coordination with Celery here because of this distinction between an async result and a group result. So Celery has a lot of branching around, if this is a group, do this thing. If it's just a regular async result, do this other thing. But you can see that apply async actually constructs a group result from the list of applied subtasks. This apply tasks generator, it just goes through and applies async on the individual task signatures and then yields each one's async result. So what you get is a group ID, which is the UUID of the group result that I had mentioned, and then all of the async result instances from the subtasks. So now we've covered chains and groups. What happens when you want to combine them? The chord is the most complex type of all of the Celery Canvas workflows. And basically what it is it's a group chained to a callback. So you have a group of tasks that are executing in parallel. And when all of the tasks are done, really when all of them have succeeded, then it launches this callback task. The group, it calls the header, and the callback task, it calls the body. So you can see the body and the header in the dictionary version of the signature. So the body task actually gets a list of all of the results from each of the header tasks. And so this tasks.tsum here would get a list as its argument passed to it by Celery. And then in this case, it would just sum all the numbers together. The result, the async results returned from executing the code is similar to the chain. It's the result for the body task. So then, when you call .result on it or .state or whatever, you'll see the state or result from the body task. And if you navigate back to its parent, it's linked to the group result corresponding to the group of header tasks. And so you have this kind of like asymmetric relationship here where the async results parent is the group, but the group's children are all the group's subtasks. You can't actually get from the group, the header group, back to the body result. So it's kind of an odd family tree. But you can see that you can still inspect each task and results from the group, get the individual results, and then they're summed together in this callback task. So this requires a fair bit of coordination from the result backends in order to work. The cord knows how many tasks are in its header group, and so it stores that as its cord size. The task tracer then, anytime a member of a group which is part of a cord completes successfully, will react in some way based on the back end of the result store that will determine whether or not the cord's callback should be executed at any given point in time. So, as I said, different backends work different ways, and this is where the atomic counter comes in handy. Because with Memcache and Redis, once the header group has been executed, then anytime a member of that group succeeds, it increments a counter based on that group UUID. Remember that group ID is distinct. And then once that counter reaches the size of the cord, then it knows that it's okay to run the callback task. It can gather all the results from all the header tasks in the cord or in the group and pass those to the body callback. For all the other backends, Celery actually launches a separate task whose only job is to poll the group for the results of its children. And if all the children are in a success state, then it knows it can call the callback task. If they are not, then it launches a retry, and it will retry with a certain countdown. I can't remember how long it is, but it'll wait and continue to poll and poll and poll until the group is finished. So you can see how it would be advantageous if you want that callback to run quickly to use a result store that supports atomic counters. So these are all of the primitives that Celery provides by themselves for composing workflows. But if you wanted to, you could have built something like chain, for instance, yourself, without any support from Celery. It's just a subclass of signature. Celery's support of the link function for linking callbacks gives you everything that you need to chain them all together. So I have created something that I call a weave that is just an example of how you could extend the already existing primitives to create your own distributed workflows. So a weave is just a custom signature subclass that takes a task and takes a numeric length of a list. It accepts a large list as its argument, as its first argument, and it splits it into smaller lists according to the list size that you specify. It passes each of those smaller lists into the task that you gave it, and it takes the results of that task, calls a join task to join the subsequent smaller lists all together back into a single big list, and returns that back to you. So in this case, range does exactly what you would expect, gives you a list of numbers, and multiply takes each member of the list and multiplies it by 2 and returns a list with each member multiplied by 2. And so you can see the kind of tracing the path of what the weave does in order to retrieve a list at the end that is the same as the original list with each member multiplied by 2. There's a little more code than I could easily fit on the slide here, but you can see I call this class decorator register type on the signature subclass, and I provide a subtask type of weave, and that tells Celery to register this signature as a type weave. So anytime it sees subtask type weave, it's going to construct a weave instance. I put weave as the second arg of the init here that arg represents the task that is associated with it, but since there's no real task associated with all these signatures, I could have put none there just as easily, because Celery is never going to try to launch an actual task for a signature subclass that doesn't have a one-to-one representation of an actual task. So in my apply async, basically what I'm doing is I'm taking an iterable from the args that I assume will be applied to the signature at some point later than its init, because I only take the task and the list size in the init. I create a chord out of this join task that I use as the body, and a group of header tasks that are cloned from my original task that I passed in. You see down here at the end, tasks.clone, and I provided an arg that's a subset of the original list as I chunk the list or the iterable into the iteration size that I want. And so I end up with a group of tasks that are all the same task with different sublists passed to them, and a join task that joins all the lists together, and I create a chord out of it, and I return that chord, and this is my custom signature subclass. So why would I do this? Well, let me give you a practical example with a Twitter API integration. The Twitter API allows you to ask for friends or follower IDs in groups of up to 5,000 IDs per API call. And because we want to consume the API as efficiently as possible, if we're trying to get all of your friends or followers, of course, we would ask for the maximum number of IDs we can get. But if we want any other information on those users than their ID, we have to request the full user object, and Twitter limits those calls to 100 IDs per call. So in order to get a full list of 5,000 usernames, we would have to make a single API call for all the IDs, and then 50 API calls of 100 apiece in order to get the usernames out of the user objects. You can see how this would be a natural fit for the weave concept that I've created. So without any special coordination, with just this weave signature subclass and those basic tasks, I can now construct a workflow which results in a single list of all of my Twitter friends' usernames based on using chaining this friend ID call to a weave containing username task with size 100. So I'm making calls of 100 IDs at a time to the user's endpoint and getting the user objects, extracting the usernames, and the join tasks joins them all back together into a single list. So this is just an example of the kinds of things that you can do with the Celery Canvas workflows by creating your own signature subclasses. So it's important to note what happens when one or more tasks fail in these workflows, because, it may be kind of unintuitive and it may be catastrophic depending on how you architect your tasks. So you need to know what happens. When you run tasks in parallel, it's pretty benign. You can get the state, success or fail for each of the tasks individually. You can inspect the results. Remember, in a group, all tasks are created equal, so nothing is going to prevent anything else from running. You just see that some tasks failed and some succeeded. If you're running tasks in series, then it's kind of like, flicking one domino out of the series of dominoes, right? Like it takes one to fall over to hit the next one. And if you've got a gap or one missing, that's an analogy to a task failure, it's not going to knock over that next domino. And all of the subsequent tasks are going to fail to run. This makes logical sense because things in series they create a dependency chain, right? And so if you have a prerequisite that it's not fulfilled, you can't run the thing that depends on it. But it's just something to be aware of. you should be very defensive in your coding about trying to retry tasks that have transient failures until they succeed, and understand that any chaining or callbacks won't run if the parent task fails. So I put together a few rules of thumb that aren't directly related to workflows, but are kind of some best practices throughout my years using Celery. The first one I feel like is pretty obvious. Never block on a task, from a task, or from any process, really. The whole idea of Celery is that it's meant to be concurrent. And if you have one process waiting on another process to finish and doing nothing, then you are wasting your concurrency. Always find ways to compose tasks together rather than blocking on one task and getting the result in a synchronous manner before moving on with your other task or the other process. That should be fairly obvious. You want to try to design your tasks to do the smallest useful amount of work. The reason I put useful in there is because there is a fair bit of overhead involved in serializing your task, sending it over the network to your message broker, sending it back over the network as a worker consumes it from the broker, deserializing before you even begin to run your function. If you do something like, I heard one company once say that they were putting all of their database writes into Celery tasks, like one database write per task, and they were seeing terrible performance, of course, because the overhead of just doing the database write in the process is less than actually doing all that work to make it a task. But if you're doing like an API integration or something like the Twitter example I showed, it's a really good rule of thumb to have, say, like one API call per task or something like that. The smallest useful unit of work that you can create will give you the best return for your concurrency buck. A lot of people don't know about the soft and hard time limits in Celery, but they can be super useful in kind of having some guarantee about how your worker pool resources will be used. If you have tasks that can in some circumstances take a really long time, maybe because Facebook is slow right now or some other resource is constrained, then it can be really useful to interrupt those tasks. And if you make them idempotent, then there's no downside of running them over again. If you've already made them small amounts of work, then you haven't lost a whole lot. All these design principles begin to work together to create a system where you are using your concurrency well, where you can fail without worrying about it. And then the time limits will give you good guidelines for good guarantees for how long your tasks will take at most before they just get axed, get killed. It's important to set both soft and hard because, as I've shown here, some tasks don't respond to the exception that gets raised for the soft timeout, and they have to actually be killed, like when a thread is waiting to join. So axe late is another underused feature in Celery. What happens when a worker consumes a task from a broker is commonly that broker will set a reservation for how long it will hold the task before reissuing it into the queue and to another worker. And the way that a worker says to the broker, okay, it's all right for you to remove the task from the queue, is by acknowledging or acking that it's received that task. Celery workers, by default, will act when they start working a task. But you can conceive of workers dying mid-process without being able to communicate back to the broker. Celery will try to revoke the task and try to send it back to the queue, but that's not always possible. Like if there's a network outage and or power outage, all kinds of things can happen, and things will just die. So when you're acting early, you can lose tasks from workers that have partially worked the task and then gone away, weren't able to revoke it, so it never went back to the queue, and now your task just drops on the floor. If you act late, the worker will not act the task until it reaches a terminal state, either a success or failure. In that case, you're guaranteed that the task will be re-executed if something happens to the worker. The risk is that if that reservation time on the broker expires before the worker can act it, then it will go back into the queue and be worked over again by another worker. So you see how this could work in tandem with your soft and hard timeouts so that you can guarantee your execution window for a task and if you are making tasks idempotent and quick and all that good stuff, then acts late will give you much better safeties against tasks being lost midstream. Yeah, that little note from the Celery doc explains it pretty well. There's another one that I didn't make a slide for, but I want to cover. In Celery 3.1, at least, the default serialization method used is pickle. I don't know if any of you guys saw Alex Gainer's talk at PyCon this past year, but pickle can do very bad things to software. And it's not only a security concern, but say for instance that you want to send a Django model instance as a Celery task, which is already a bad idea to begin with. If you're using pickle and you send your task to the broker, it serializes everything as well as it can, and let's say it's in flight and you do a database migration or a deploy or something that changes the model somehow, right? The model instance will get unpickled or reloaded with its old class definition, and you now have Celery tasks that are running against some class definition that doesn't match it, and bad things will happen. This is the problem with pickle in general. So and a really easy solution to this is to just use the JSON serializers. Not only will that avoid all of the security concerns with arbitrary code execution that pickle potentially has, but it will force you to use task arguments that are JSON serializable. And I feel like that's just good for everybody. In fact, so did Ask, because he made it the default in Celery 3.2 and actually warns you, gives you a big nasty warning if you use pickle in 3.2 or later. Yeah, so I think that's about all I had. So now I'll take any questions you guys have. Or I can keep talking about Celery stuff that's not on the slides. Yeah.
The return value of the signature, what is that? Didn't pull up. So I mean, is it a string or is it?
What do you mean by signature is a class? So what do you mean by the return value of a signature?
So when you call this, it goes to your building. I'm just curious if that is an item or a deterministic thing, or if I call the same signature with the same arguments, is there any way to tell that I've done that? Are those deterministic in that if I generate two of them, compare them, can I tell if they were called identically?
The question was how do you determine signature equality? Is that kind of what you're saying? Okay, the under EQ, it doesn't traverse the args and quargs to determine if the signature is effectively the same, like if it's pointing at the same task. So if you do signature tasks.add.s12 equal tasks.add.s12, then it'll give you false because it's looking at the Python object IDs. So unfortunately, that's not implemented, though it could be pretty easily, I feel like. But one thing that you can do is if you are passing a signature around and you are afraid of two different processes trying to run that same signature, what you can do is freeze the signature. And the .freeze method will go ahead and assign a UUID for the task ID for that specific signature, and it will give you back an async result instance. And so then anytime you get an async result back from that signature in the future, it'll use the frozen async result. And so that can be useful to prevent or at least so that you can tell that the same task was run twice, because it'll run with the same task ID. Things will get really screwy, but at least you can tell. Yep. Yes?
I have a question about a scenario that I'm encountering implementing Celery. And my objective is I'm adding multiple items to the task queue, but I want an ability to be able to reduce multiple items into a single worker process, opposed to having each one of the items in the task queue go to their own individual worker process. Is there anything that can reduce multiple items into the queue into one process?
So tasks, the question was, can you reduce multiple tasks to be worked in the same process, right? tasks are meant to be independent units of work, like not really related to other tasks unless you're actually explicitly relating them together. But what you can do is you can determine either in real time as you're launching the task or ahead of time in the task definition what queue that task is intended to go to. And then you can have different worker pools working different queues. You can have a single worker pool working as many or as few queues as you want. So if you want to make sure that the same Celery process, the same Celery worker is going to run all of these tasks, you can create a queue specific to that worker and send those tasks through that specific queue. Now, it won't like squash all of them down to run only one function. It'll run still task after task, but at least you'll be in the same process space. Does that help at all?
Not really, but
Okay.
I realize that there's probably going to have to be a solution that goes outside temporarily to store all of those processes, possibly in Redis or some other information store, and then pull them all into one individual process as it's but no, thank you. No, I mean, yeah, it's a good thought that'll help me keep thinking about my problem.
So, I mean, you could have, I don't know, some sort of, counter or some external state that is a flag for, how many of these are in flight right now, or some sort of distributed lock. There are different mechanisms you can use on top of Celery, outside of Celery, to help control the flow. I don't know your specific scenario, so.
Right, something I'm going to have to keep looking into.
Yeah. Yes.
Yeah, is anyone observing something, I guess, on the level of what you call the weed, in a graphical console?
Is anyone generating callbacks into a graphical console to like observe the progress of what I think was presented as a weave?
So in a graphical way, the only thing that you have at your disposal is Celery does provide methods that will create a graph visualization out of a async results dependency tree. So you have .children and .parent, and that creates an inherent graph, right? And you can create a graph visualization. It's kind of expensive to do, so I don't think anybody's doing it in real time. Celery does have a monitoring tool called Flower, in which you can, it's a web interface to be able to track what tasks are in flight. There's a URL endpoint for each task UUID, so you can see how that task kind of progressed, when it started, when it ended. And I think you can link to parent and child tasks from within that. So you can use that web monitoring tool to kind of stitch together your own, internal visualization of what's going on. But the graph viz output is the closest thing that Celery has to support of a graphical view of that.
Thank you.
Any more questions?
I mean, I can keep talking about stuff if you want me to.
You're very welcome.
I go on all day. Obviously, when you're working in a distributed system, log collation becomes really important, because you want a single place to look for where did this thing get run. So just a quick shout out for Heroku. Our log collation is awesome. So you can see all of your dynos, your worker dynos, collating into a single log point, and then drain that to wherever you want to. So then if you're using a tool like Flower and you want to know what happened to this task, I want to see the log output, then just take the UUID and using Loggly or Splunk or whatever, you can actually search for that UUID in your collated logs. And that's really the only sane way to debug Celery stuff, because you never know where something's going to run. You often can't reproduce issues locally that you had in production. And so I really recommend log collation, being able to search your logs, and keeping track of your task UUIDs somewhere. And the answer to almost all bugs in distributed systems is more logging. Things can almost always be solved with the right logging and more logging. So I really highly recommend that. Additionally, there are debugging tools that work best locally. There's this PDB variant in Celery called RDB that will allow you to set a breakpoint inside a task and will actually open telnet on a port, a unique port per task. So you could have 10 tasks running in parallel in a group, set a breakpoint, an RDB breakpoint of those tasks, and it'll launch 10 telnets on different ports. And you can actually telnet into your Celery process and then poke around just like you would with PDB. And that can be really useful for debugging. Yeah, what else? Yes? About Heroku? Brokers. Oh, I'm just hearing what I want to hear. Yeah, so, oh, you want to know where we were? Yeah. Yeah, I said I didn't talk much about brokers. So the only thing I have to say about brokers is that if you're using anything but RabbitMQ or Redis, you're asking for trouble. Because even though there is support for things like, SQS and IronMQ and CouchDB and Mongo, they're not fully supported. Like there are features that are going to be missing. There are things you can't do. Like this flower monitoring tool only works with RabbitMQ and Redis brokers. I prefer RabbitMQ because I feel like it's a tool made for the job, but it's also more configuration to set up, and some people don't like the configuration hassle. If you don't have your file descriptors bumped up in your file system, then you can crash Redis or RabbitMQ. Sorry, if you have a ton of tasks or a high queue depth. There are different things that can go wrong. It's operationally more intensive to run RabbitMQ, but I feel like it's the best tool for the job. Redis is good enough to the point where I don't know, it's not a huge deal if you want to run Redis as your broker, but I wouldn't run any of the other ones.
Thanks.
Cool. Well, if you guys have any more questions, I'll be here in Ohio for another couple of hours at least before heading to the airport. So just track me down. And, if you're looking for a job, as we all are, I'm sure, we're hiring.
Thank you, David. Thank you for the great presentation.
Thanks.